Hello, everybody. My name is Christian Canales, and I'll be going over question number 2 on Chapter 5's homework. So in Part A, it asks us, in a modified version of the cart and bucket in Figure 1, the angle of the slope is 34.9 degrees, and the bucket weighs 215 newtons. The cart moves up the incline, and the bucket moves downward, both at constant speed. The cable has oh my god. Okay. has no important mass or whatever, and there is no friction. What is the weight of the cart? Express your answer in proper units. So for this equation, we're gonna write this one out. T equals the weight of the bucket, and that equals W cart sine of that angle. And then we're going to solve for the cart, the weight of the cart, by just rearranging. And then we're gonna just put in the numbers that we know, or the not the numbers. We're going to plug in the numbers that we got. Okay. And then with that, you're going to calculate it all, and that will equal 374 newtons, 0.8. But then we're going to round it up to 375 newtons. So that is your first answer. That's the first answer of Part A. Just using the equations that we know from the textbook. And then, so we're going to find the tension in the cable now. So that'd be T equals W bucket, right? And so, since we know that already, T will just equal 215 newtons. So you can take away from this that constant speed is no net force, and that the forces must be balanced. And then the weight of the cart was found using the force balance along the inclined plane. And the tension on the cable is always equal to the weight of the hanging bucket. Okay, so now we're on Part C, which is just going to be finding the weight of the cart again, I believe. So they give us the inclined angle of 27 degrees, and then the tension in the cable is 135. There's no friction, and that the system is at a rest, meaning the forces are balanced, which is Newton's first law. So we're just going to set it all equal again. W cart sine of angle, or whatever that one is. I'm going to rearrange it again. And then we're just going to plug in the numbers we know. So the weight of the cart will equal 135 over sine 27 degrees. And then if you do the math for that, it'll equal 297.4 newtons, which you're just going to round down to 297 newtons. That is the weight of the cart, given the tension and then the angle. Okay. That's pretty much Part C. Yep. And then finding, for Part D, we're going to find the combined weight of the cart and bucket. The total weight of the system is simply W combined equals W cart plus W bucket. So just the weight of the cart and the weight of the bucket is what the combined weight would be, obviously. So we know the weight of the cart is 297.4 newtons, right? And we know the weight of the bucket is 135 newtons, since it was stated earlier. And also, if you didn't know that, then you would know that the tension would equal the weight of the bucket, as given from our last problem. So we're going to combine those two, and that is going to get you 432.4 newtons. And then we're going to round it to 3 significant figures. So that'll be 432 newtons. That is the weight combined. We're just gonna get some takeaways from that. It would be the equilibrium condition that forces our balance since the system is at rest. We found the weight of the cart using the force component along the inclined plane, and the total weight is simply the sum of the cart and the sum of the bucket's weight. Okay. Now we're going to go on to finding the required angle of the slope. So we're given the mass of the cart. This is part E, by the way. Mass of the cart, 175 kilograms, right? Now we know the mass of the bucket, which is 55.0 kilograms. We know there's no friction. It's constant speed, so forces are balanced, so there's no acceleration. And we know that G is going to equal, obviously, if you don't know this by now, then I don't know. So since the system moves at constant speed, the forces must be balanced. That would be T equals W cart sine of theta equals weight of the bucket. W equation for that. W cart equals M cart G, which is simply 175 times 9.81, and then that will give you 1,716.8 newtons. And then to find the weight of the bucket, you do the same thing. That'd be 55 times 9.81, and then that will give you 539.6 newtons. And since the system is balanced, that would mean the weight of the cart sine theta equals the weight of the bucket. Now we're gonna solve for sine theta. Goes the weight of the bucket over weight of the cart, and then equals 39.6 over 1700, 16.8. Should average out to be like 3143, and to find the angle or separate the angle, you're going to make it inverse of that angle, of that number, and that will leave you out to be 18.3 degrees. It is going to be the final answer for part E. So that's pretty much just using all the equations that we've been using before. This is what was given to us. These are just basic rules of physics here. And then this is just the work for it. Not too hard. That's more of the, that one was more of the like, I don't know. That was a very, not hard problem, it was just a very tedious one, since you need to find lots of moving parts. So we're going to find the tension in the cable. As we all know, the tension in the cable is just the weight in the bucket. So that is just going to equal out to be 540 newtons will be your tension in the cable. Just because we're going to round up. We're going to round up 3 sig figs. Here's the key takeaways you should take from this. The constant speed is no acceleration, and that constant speed equals no acceleration, and it also means that forces must be balanced. Slope angle is determined using the weight ratio and sine function, which we did, and the tension in the cable is equal to the bucket's weight in equilibrium, as always. This problem shows a realistic application of Newton's laws and force balances on an inclined plane. So I think this is the final part of this. I believe this is the final part of this question. It's just going over part G. Let Let me check. Oh, let me check my. No, it's not. Okay, part E is not the final. But to understand the problem, you know that the cart and bucket have the same weight. The system remains at rest, which is then F force equals 0. And then that friction is present, which helps the cart from sliding. So the component of the cart's weight along the incline is W cart parallel equals W sine angle. Alright, so then the tension on the cable also equals T equals W, and friction force is T plus F, fancy F equals W sine angle, and then W plus F equals W sine angle, right? Then we're solving for F again, so that'd be F equals W sine of angle minus 1. So that would be F equals W1 minus sine something like that. And then that would be your answer, because this ensures that the friction is a positive force. Let me just clean this up a bit. This ensures that friction is a positive force, balancing the forces parallel to the incline. That one was just asking us to make an equation of what the magnitude of the friction is on the cart using terms that fancy A and W. So that's pretty much that. This ensures that, static equilibrium. Forces must be balanced out for no motion. Friction direction. Friction must counteract the imbalance in forces. Absolute fix ensures that friction is always positive. Okay. So for part F, not F. What? Part H. Part H is asking us, is the friction force less than, greater than, or equal to W? That's from part G. I believe what I put for this one is that friction was less than W. And that's simply because the friction force is always less than W, except when this angle equals 0 degrees, where F would equal W. So that means F will be less than W. That's just because the inequality that we solved, that we have from the other one, just that is the basic rule of that. So that was pretty much all of that's pretty much all of it. That was pretty much all of question 3 or 1. I'm not too sure. I forgot which one this one was, but that should be all that. I think it was 2. Yeah, this is question 2. So that was question 2 of chapter 5's homework, and it was a pretty easy one. It was pretty much easier than the other ones that we've done. But thank you for taking the time out of your day to watch this, and hope to see you guys